Hello, everyone. Welcome to part 2 of network theorems. Last time we covered what network theorems are, and we touched on Ohm's law. We touched on KCL, Kirchhoff's current law, and then today we'll be touching on KVL, which is Kirchhoff's voltage law, which incorporates a bit of everything. So Kirchhoff voltage law, it states that the total amount of voltage around a loop sums up to 0. So the sum of voltage while passing through the clockwise direction must sum up to 0. So I will show you based on this example over here. So within the example we have V over here, which is two resistors in series. So we have this loop that is our clockwise direction. We have positive there. We have so it means that VAB, which is the voltage across this resistor, plus VBC plus this V, which is our source, should equate to 0. But something interesting happens here. Since our loop is a clockwise direction, so that clockwise direction, it accounts for our current direction that we assume. So we know current flows from positive to negative. So in this assumption, this current flows in that direction, thus that V will be equal to 0. So we all know in Ohm's law, it states that the total amount of voltage across each resistor in a series circle sums up to be equal to the source voltage, which is equal to V is equal to VAB plus VBC will be equal to V. And then in this, whatever value of V is, it will be a negative in this scenario because of the placement of that V. So we'll go over some scenario that will show us how this actually works. And we'll move over to the next slide. So in Kirchhoff voltage law, we have something called a loop analysis. So there are some steps you need to take into account when we're dealing with Kirchhoff's voltage law. We need to identify the loop, if is it clockwise direction or anti-clockwise direction. And then so pick currents into clockwise direction, set up the loop equation, and solve systems of equation. And then you will obtain your currents over there. So just like in this example over here, so the loop 1 is in our clockwise direction. So what's interesting is that we are given our current direction. I1 is flowing that way, I3 is flowing that way, and I2 is flowing that way. If you remember Kirchhoff's current law, no current accumulate at any node. So it would be this direction, because we are given our positive and negative of our resistors. So once we are given that, we can tell from negative to a positive, from negative to a negative. So there will be a negative value within one of those there. So in this situation, the sum of this voltage will be V R1 plus VR2. But the interesting thing here with VR2, there are two currents that are acting upon this. We have the current in loop 1, when we have also the current in loop 2. So addition, so I, the voltage across there, let's say VR2 would be equal to, let's say, I'll say this is I1, which is for loop 1, times R2 plus I2, which is from loop 2, R2. So R2 is I1 plus R2. That will be our formula for VR2 in this case. And then we'll move over to the next for an exercise. So we have this exercise here. So in any form of a circuit, it is a complex circuit, which is, it's a network theorem. It's a complex network. So what we need to do is we need to simplify it even further. So in this exercise, we see where we have our voltage over here. So looking at this source, we have that direction and that direction. One of them sends current, one of them receives current, because current flows from positive to a negative. So if we are looking towards, if we are looking at this direction of our circuit, there is this current that will be flowing here, and it splits. So our total resistance, let's say total resistance for this section over here, it's calculated by 6, which is 6K, plus 6, which is this resistor and that resistor. They are in series, in parallel with this 6 kilo ohm. All of them, they are kilo ohm, which will give us 4 kilo ohm resistor. And then we have the same thing on this side. We have the 6 kilo ohm and the 6 kilo ohm in series, and we have this in parallel with that. Therefore, this section over here, it's going to be the same, plus 6 parallel with that 6K, which will give us 4 kilo ohm. Then if we redraw our circuit, we will have kilo ohm and 8 volts over there, which makes these two in series. We'll be able to then thus calculate our total current, which the current will be given by IT is equal to V over RT. V over RT is given by 4K plus 4K. We have a total current of 1 milliamp flowing within our circuit. And then, yeah, that would be our total current in the circuit. Once we have our current, it should be easy to get the rest. So that's how our circuit analysis would work. If we move over to the next slide. In the next example, we have this circuit over here. In this circuit, we have two supplies, three in fact. We have below. Okay, let me write on the side. We have VAB if we choose a loop. We have VAB plus VBC, which is given by 8, 0.8 VBC plus CD. VCD plus, well, there's nothing there, it's already 0. And then we have EA, VEA. VEA, which is equal to 0. Then, if this is I1, or I, in fact, if this is I for this particular loop, then I multiplied by 2 ohm will give us I multiplied by 2 ohm will give us VAB. And then VBC, it's given by 0.8 plus VDC, it's given by 2. If you look at it like so, the positives, these are positives because from negative to positive, but from negative to negative, that's where things change for VEA, which makes VEA negative 3 volts, which is equal to 0. And our current direction is in a clockwise direction. And thus, that resistor has a positive to negative, positive to negative, from positive to negative, and then from negative to negative, which makes that 3 volts equal to -3, I mean. And then what we are aiming to get is what the value of I is for our circuit. So we will add this and take them to the other side. Here we have 2I, which is equal to 0.8 plus 2 minus 3, which is negative 0.2. Move it to the other side of the equal to sign. We have 0.2 positive. Then divide by 2 both sides. Divide by 2. We have I is equal to 1.3 amps. That's our I total for this particular circuit. So what's really interesting about this is choosing the loop and noting which of our voltages will be on the negative or which ones will make a positive. So there is this particular example, which is part of one of the practical components that I will be also doing, but we'll start off with calculation. So we have two supplies. We have V1 and then we have V2. So we will have 3 loops in this particular exercise. We will have this loop. We are going to term as I1. We have this loop. We're just going to choose all of this as clockwise direction. And then we have this loop as I3. I hope we remember the circuit. I will end this video here for now so that we start off on a new video for our calculations concerning this circuit. Thank you.